So here we go. Here are the values, and we are now in the center of mass. I'll just put CM, frame. And what do we get? Let's find the total initial momentum. P initial will be 6 kilograms times 2 meters per second plus 4 kilograms times negative 3 meters per second. And again, what do we find? 6 times 2, 12, minus 4 times negative 3, negative 12. Total initial momentum, 0, as we expect for the center of mass frame. What is the velocity of the center of mass? Again, 0 total momentum, 0 velocity for the center of mass. What is our kinetic energy? Now, remember, in the center of mass frame, the kinetic energy we are determining is the relative kinetic energy. So this will be K rel, and we're looking at initially, and what do we get? We'll get 1/2, 6 kilograms, times 2 meters per second squared, plus 1/2 times 4 kilograms times negative 3 meters per second squared. And what do we get? 1/2 times 6 times 2 squared is 12 joules. 1/2 times 4 times negative 3 squared, that is 18 joules. And what do we get? 30 joules. So again, remember, the kinetic energy of the center of mass initially was 180 joules. And we did find that, we have the KCM initial plus K rel initial, which is 180 joules plus 30 joules is the 210 joules, which we did find to be the total initial kinetic energy. Okay, there we go. So again, initial kinetic energy equal to the sum of the kinetic energy of the center of mass plus the relative kinetic energy. Okay, very good. And then one more. What is U rel? I'm running out of room down there. I'm just going to put it up here. What is U rel? Initially, that's going to be U2 initial, negative 3 meters per second, minus U1 initial, 2 meters per second, which again is negative 5 meters per second. Okay, so same U rel as we had before for the elastic collision. Okay, great. Let's stick all this over here and let's do the same for the final situation. So finally, we have P final equals 6 kilograms M1 times U1 final, negative 1 meters per second, plus M2, 4 kilograms times U2 final, 1.5 meters per second. And what do we get? 6 times negative 1, negative 6 kilogram meters per second, plus 4 times 1.5, 6 kilogram meters per second. And we end up with a total final momentum of 0, as we would expect again. What is our velocity of the center of mass? Finally, again, 0. Okay? Total momentum 0, velocity of center of mass 0. What is our final relative kinetic energy? We have 1/2 times 6 kilograms times negative 1 meters per second squared plus 1/2 times 4 kilograms times 1.5 meters per second squared. Multiplying this out, what do we have? We have 3 joules plus 4.5 joules, which is 7.5 joules. Now, notice, 7.5 joules. That is less than the initial relative kinetic energy. So what's happened? We have lost relative kinetic energy. But what is the kinetic energy of the center of mass? It's still the same. Those values are still the same. Where the energy has been lost is here, in the relative kinetic energy. Remember, what was KCM? That was 180 joules. And total initial That was initial. Total initial kinetic was 210 joules. 30 plus 80 gave us 210. Now, with KCM final, which was the same as KCM initial, that was 180 joules. And what was the final kinetic energy? It was 187.5 joules, which again is 7.5 plus 180 is 187.5. So, KCM, still the same. Where did we lose the energy? In the relative kinetic energy. Okay, and then what is U-rel final? Hopefully you can see down here. U-rel final. That is 1.5 meters per second minus -1 meter per second, which is -2.5 meters per second. Okay, so U-rel final is -2.5. Oh, I'm sorry. No, the negatives cancel. That is positive. Sorry. Positive 2.5 meters per second. Notice that is equal to V-rel final. So we get the same relative velocity in the regular frame, the first frame, and the center of mass frame, exactly as we found with the elastic case. But it is not the same as the relative velocity before the collision. So the relative velocity, well, it's not, obviously, it never is, but it's not the negative of it. That's the important thing. We go from -5 to a positive 2.5. The receding velocity is less than the incoming velocity. So again, what's happening here? We have the two masses coming in the regular frame, it would have looked something like this. But now in the center of mass frame, we see they come in fast and then go out slow. So fast, slow. We have lost some of that velocity, the relative velocity. Okay, very, very good. So let's think about this one more second here. Where did we lose energy? We lost energy in the relative kinetic energy. Is it possible to lose more? How much can we lose? Would it be possible to lose all of it? Well, let's think about that. Would it be possible to have no relative kinetic energy? Well, the relative kinetic energy is 1/2 m U1 final squared plus 1/2 m U2 final squared. What if U1 final and U2 final were both 0? Is that possible? Is it possible for both U1 final and U2 final to be 0? As a matter of fact, it is. Let's take a look at one more example where we lose the maximum amount of relative kinetic energy, which would be all of it. That's what we call not just an inelastic collision, but a maximally inelastic collision. A collision that loses as much kinetic energy as possible. Let's take a look at that one. So again, the initial situation, exactly like we've had before. I will not force it to go through all these derivations again. Let's just look at them. Total initial momentum, 60 kilogram meters per second. Velocity to the center of mass, 6 meters per second. Total kinetic energy, initially 210 joules. Of that 210, 180 joules is in the motion of the center of mass of the system. 30 joules is in the relative motion of the masses around the center of mass. And the initial relative velocity, -5 meters per second. Now here is the final situation for a maximally inelastic collision. Let's take a look at this. What do we have? Final momentum, total final momentum. Again, sum of the momenta, the final momenta of mass 1 and mass 2. So M1, 6 kilograms times 6 meters per second plus 4 kilograms times 6 meters per second equals 36 kilogram meters per second plus 24 kilogram meters per second. 36 plus 24 is 60 kilogram meters per second. Once again, same final total momentum as the initial total momentum, as we would expect. Velocity to the center of mass, again, same 6 meters per second. We have the same total momentum, same velocity for the center of mass. What is our final kinetic energy? 1/2 6 kilograms times 6 meters per second squared plus 1/2 4 kilograms times 6 meters per second squared, which is 1/2 times 6 squared is 108 joules, plus 1/2 times 4 plus times 6 squared is 72 joules, which gives us a total of 108 plus 72, 180 joules. That is an interesting result. What do we notice? That total final kinetic is the same as the initial center of mass kinetic. Okay, let's take a look at that. What is our kinetic for the center of mass? Finally, 1/2 times the total mass, 10 kilograms, times the velocity of the center of mass, 6 meters per second squared. Multiply that out. What do we get? We get 180 joules. All of the kinetic energy is in the motion of the center of mass. We'll look at the relative kinetic energy once we transfer into the center of mass frame. I just wrote that down here. We know this, we get this from the center of mass frame, but we've already looked at this, so we know what that's going to be. But we'll look at what the relative kinetic energy is in the center of mass frame, okay? And then VREL final is V2 final 6 meters per second minus V1 final 6 meters per second equals 0. 6 minus 6 is 0. We have the same final velocities for both masses. What's going on here? What happened in this collision? Well, what happens is, in order to end up with the same final velocity, we've got these two masses coming in and doing what? What do you think? They're sticking together. So, as they come in and they collide, they then move off together as a unit. So, imagine these two things not as bouncy balls like this, but more like maybe balls of sticky clay or putty or something. So they come in and they stick together and move off as a single unit. Okay? We'll see that a little bit more in the center of mass frame. We'll see how that works out. Okay, very, very interesting results. Let's take a look at this, the same thing in the center of mass frame. Sorry, before we move ahead, we need to figure out what are the velocities in the center of mass frame. So again, velocity of center of mass, 6 meters per second. So we need to subtract 6 from all of these, and what are we going to get? We're going to get U1 initial is, again, 8 minus 6, 2 meters per second. U2 initial, 3 minus 6, negative 3 meters per second. U1 final, 6 minus 6, 0 meters per second. U2 final, 6 minus 6, 0 meters per second. Okay, so this is interesting. Let's take a look at the center of mass frame. Again, we've seen this before. In the center of mass frame, and let me write that down, so this is now in the center of mass frame. For a maximally inelastic collision, again, we have total initial momentum 0, velocity of the center of mass 0, the relative kinetic energy 30 joules, the relative velocity negative 5 meters per second, and remember the kinetic energy of the center of mass from the initial frame was 180 joules, where the total kinetic energy was then the sum of K-rel and the center of mass energy, giving us a total of 210 joules. Now, for the final situation. Final situation for maximally inelastic collision in the center of mass frame. What do we have for the total final momentum? Well, we've got a velocity of 0 and a velocity of 0, so that's going to give us 0. Well, that's not a surprise because we expect it to equal this, velocity to the center of mass, again, 0. What is our relative kinetic energy finally? Well, we've got 0 velocity here, 0 velocity here. The relative velocity is 0. The relative kinetic energy is 0. We have no relative kinetic energy. Let's just finish and then we'll come back and think about that. Now, remember that from the first frame, not the center of mass frame, we found that KCM initial was 180 joules. And the total, that's final, KCM final, and the total final kinetic energy was 180 joules. So what we see is that all of that kinetic energy is in the motion of the center of mass, and none of it is in the relative kinetic energy. And then finally, UREL final is 0 minus 0, it's 0. There is no relative velocity. They are not moving apart. They are not moving toward each other. They are moving together. In other words, what's going on here? In the center of mass frame, we have M1 coming in, and M2 is going to be moving a little bit faster. So we've got M1 moving a little bit slower, M2 moving a little bit faster. What happens? They stick together, and then what do? They just stop. Both of them stop. They come together and collide and just stick together motionless. So that the center of mass is now stationary relative to the masses. Well, the center of mass was always stationary relative to the masses in the center of mass frame. But now both masses are just stopping. So actually, we shouldn't even put these little arrows here. And to be honest, we should draw them stuck together. They are now stuck together as a single object, you might say. So M2 is now over here stuck to M1. Like that. The two masses come together, stick together. Very, very interesting result. So we've looked at a number of examples here. We looked at a general collision in a general frame that was completely elastic. We looked at it initially and finally. Then we looked at it initially and finally in the center of mass frame. Then we looked at an inelastic collision in a general frame, initially, finally, and then in the center of mass frame, initially and finally. And then we looked at a maximally inelastic collision. We looked at it in the general frame first, initially and finally, and then we looked at it in the center of mass frame, initially and finally. Okay, wow, those are a lot of examples. What we're going to do now is we're going to take a look at a way of kind of determining whether or how much a collision is either elastic, if it is elastic, or is it inelastic. And if it's inelastic, how inelastic is it? A little bit inelastic so that it's almost elastic, or is it maximally inelastic, where it loses as much kinetic energy as possible? Okay, let's take a look at that.